Hi, so in the last video we said that you can take a mechanism and you can use it to deduce a rate law. And remember earlier on in this course we said a rate law is always something that you've got to measure experimentally. But we can make a prediction from a written mechanism, from a proposed mechanism, what the rate law should be. And if it matches up, that gives us some confidence that maybe we know what we're talking about. So the elementary reactions are classified according to the number of collisions that take place inside of them. And we call the number of reactant molecules colliding the molecularity, which is sort of a mouthful, huh? So let's write down some reactions here. So imagine we have an elementary reaction where a molecule A shakes itself apart and forms products. Since this is just essentially the collision of one molecule, which I know is kind of like the sound of one hand clapping, but anyway, we call this a unimolecular elementary reaction. Now imagine we've got two reactants colliding, so we could write it as A plus A forming products. I'll just write P. We could sometimes write that as 2A forming products, or they could be different molecules, A plus B forming products. So if these are the elementary reactions here, we would classify all three of these as bimolecular because there's two molecules colliding or two species colliding in the elementary reaction. I want to point this out, though, that when you've got 2A, that is shorthand for A plus A. So we often write it this way, and sometimes people forget that this is actually just the same thing as this. If we have three collisions, so this could be three different molecules, A and B and C, okay, or it could be two of one and one of the other, or it could be three of one. So all of these would be classified exactly the same way. We would call these molecular. So ter, short for tertiary, so that is three, so molecular. Okay, elementary steps or elementary reactions. So just make sure you're aware of the fact that when we use coefficients, right, that is just a way for us to avoid writing A plus A or A plus A plus A and so on. So those are the molecularities. Now what we typically find is that bimolecular is extremely common. So it is very common for two things to bump into each other and react. We find that three things bumping into each other is less common, so it turns out that it's not too uncommon for two things to bump, but for three things to bump into each other simultaneously is unusual. And think about it. I mean, you probably went grocery shopping and you've probably walked around the store and seen someone you know and stopped to chat. But when was the last time you bumped into two people that they just happened to coincide upon the baked bean aisle all at the same time you were there? That's a very large coincidence. So the fact that three molecules can bump into each other in a short period of time is so unusual. Most of the time we are looking at bimolecular reactions and in chemical kinetics. So now we've got names for these different types of elementary steps, and what's really exciting about all of this is that the rate of each elementary reaction, of each elementary step, is proportional to the concentrations of each reactant multiplied together. So what do I mean by that? Well, if I look at the unimolecular reaction at the top, I can say the rate of this reaction, I'll just write R for short, is equal to the concentration of A. I said it's proportional to, and the proportionality constant is the rate constant. Now, if I look at the bimolecular reactions, I know that the rate of them is equal to the product of all the concentrations. So if I've got an A and another A, that's A times A, or A squared. So the rate is going to be equal to A squared. Okay, and the proportionality constant is my rate constant. For my second one, that's exactly the same, right? Because A plus A is exactly the same as 2A. And for my third one, my rate is essentially going to be equal to a rate constant times by A times by the concentration of B. For my termolecular ones, it's exactly the same. So my rate is going to be K, the proportionality constant, the rate constant, A times B times C. And for the second one, the rate's going to be K times by A, or A squared times by B. And for the third one, right, the rate is just going to be K times by A times A times A, or A cubed, like so. So that's really cool. So you should be a little bit worried because up to now, right, we haven't been able to write rate laws down for reactions. But if they're elementary, if those are the actual molecules colliding, you can in fact do so. So go forth, be careful, write rate laws as long as they're elementary reactions. Thanks.